Okay, some good news this week. The content this week is less, certainly, than the igneous and the sedimentary rock section. So metamorphic rocks aren't as common. They form under specific conditions. And so there's not as much information to go over. And sometimes it's a little complicated, so maybe a little beyond this class some of the information. So I'm going to dial it down a little bit and just kind of give you the basics of what's going on here. So when we look at metamorphic rocks, we can see in our whole little rock cycle here, we've kind of covered our igneous rocks, both intrusive and extrusive. We've gone through some weathering processes. We've gone through lithification and sedimentary rocks. So our last here is our metamorphic rocks. And the idea is that a metamorphic rock is a rock that has been altered from what it used to be. And it can have started out as anything. It can be an igneous rock, either intrusive or extrusive. It could be a sedimentary rock. It can even be a metamorphic rock. As long as we're altering it from its original composition or original shape, original whatever it was. If it was a sandstone, I can alter it. How do I do that? Well, mostly we're altering things by either heat, pressure, or fluids, and usually a combination of all those things. So why do we care about metamorphic rocks? Well, just like all the other rocks, they tell us a story. And so it's one of the things we want to pull out from all of our rocks is what is it telling us about the history of the earth. So that's just useful knowledge to understand how things have occurred in the geologic past. Of course, a lot of things lead to other bits of information, like when we talk about sedimentary rocks, we said finding fossil fuels and water. These are things that are associated with sedimentary rocks. Igneous rocks can give us lots of concentrations of metals and things like that, so that's kind of useful. And so same thing, there's some properties and things about metamorphic rocks that are useful to us. It tells us what's happened in the geologic past, what type of boundaries used to exist in different places. And of course here in Arizona we have lots of metamorphic rocks that can pop up here and there. And if you've been to Pastoa Peak, you've been walking on some metamorphic rocks. If you have ever hiked 4 peaks, the 4 peaks themselves are actually metamorphic rocks. And down in the bottom of the Grand Canyon, there's also some metamorphic rocks exposed there. So we're changing our existing rocks from one rock to another, and we're doing that with pressure, temperature, and fluids. And almost always there's a combination of these three. Now, one might dominate over another, so in some instances pressure is the bigger driver. In other cases temperature is the bigger driver. In other cases fluids the bigger driver. Does that mean that there's no pressure or fluids when temperature is the driver? Well, no, but it means that temperature in that instance is the big agent of change, and that's what's causing the rocks to alter, or pressure is the bigger or fluids. You get the idea, right? Okay. So we can take, in this case, this is a picture of a mudstone, a sedimentary rock, and we can alter that into a slate. And sometimes the change isn't very dramatic, and certainly in the field it can be hard or difficult sometimes to identify a metamorphic texture or metamorphic rock because it can look very similar to its original rock, but there's some clues that can help us with that for sure. So let's see. So all this is happening, let me go back, sorry, in the solid state because the fluids are allowing the rocks to move, the elements in there to kind of move around a little bit, and we're kind of heating it enough that it doesn't melt, but it's pliable enough that we can move some things around. Some of the minerals can rotate and shift. The fluids can help some of the elements kind of break their bonds and move a little bit, but we're not liquefying this. We're not turning it into a melt. If it gets temperatures hot enough, we actually would melt it, and then when it cooled, it would be an igneous rock because that's the definition of an igneous rock, right? So when we look at different types of metamorphism, we have ones that are high heat, and we're going to call those contact metamorphism. So on this chart here, temperature increases to the right and pressure increases down to the bottom of the page here. And so there are lots of different types of metamorphism. Usually it's easier, and we kind of do this in lab, where you want to kind of get the end members. So there's everything in between. Sometimes it's useful to talk about the two end members, and that would be what we call contact metamorphism, where heat is the dominant force that's causing the change here. Even though there's some pressure, there's certainly some fluids here, but the heat is really what's causing the rocks to change. Or on the other extreme, where we have the pressure is the huge driver. So not super hot, but high pressure that's causing the change. So we see in subduction zones, so a collision between two plates, we see this type of metamorphism occurring because we're taking something and pushing it deep into the earth. It's a cold rock at the surface. It's moving down into the earth relatively quickly, so it doesn't have time to get really hot. But the pressures are extreme because these collisions are a lot of pressure as the two plates collide into each other. And so this is the driver for the change here. And of course, we have places where we have high pressures and high temperatures. Once again, the pressure usually dominates and gives us a feature that we can use to identify it as a metamorphic rock, which we'll talk about in just a second. But when we talk about temperature, where do we get temperatures, high temperatures? Well, we said that contact metamorphism means that usually it's coming into contact with something super hot. And one of the best things we can associate contact metamorphism with are these magma bodies. So remember, wherever we have a process that can cause the mantle to partially melt, we can create magma. So that would be hot spots. That would be divergent plate boundaries. That would be convergent plate boundaries where we have subduction. And so anywhere we're generating molten rock, we can cook the rock around it in a contact. So the idea would be as these little plutons or molten material rise up and they collect, they get a little bigger and bigger. As they're moving, they're intruding into existing rock. So certainly they melt some of the existing rock and it gets incorporated into the magma. But in some cases, when the magma kind of stops moving and kind of hangs out because it's losing too much temperature, it's cooking the rocks adjacent to it. So the idea would be this would be a igneous rock. When it cooled and crystallized, it's igneous. This out here, a sedimentary rock. But in between, I have a metamorphic rock where the heat was high enough to alter, in this case, a limestone and turn it into a marble. It has been altered from what it originally was, but it hasn't melted. And so this is my zone of metamorphism around a pluton. And so this is where we mean by contact. It's coming into contact with some high heat. And so that's the driver here under contact metamorphism. So if we can look at a rock and say, hey, I think this formed under contact metamorphic conditions, we're arguing that the heat has probably caused this to be changed and turned into a metamorphic rock. Now, pressure can also, of course, we said another driver can change rocks. And what we see here is showing you a little bit of what's called confining pressure. Now, confining pressure is not really what's giving us this metamorphic conditions. It's usually what we're going to call differential pressure, because confining pressure is just in all directions, right? If you go if you're swimming and you go down the pool, you can feel your ears pop maybe, or you feel the pressure is kind of coming from all directions. We typically associate pressure with metamorphism is differential pressure, where the pressure is higher in one direction than in another, because what we're going to see is a texture develops from this type of metamorphism, where we have a high differential pressure. And so what that means is we get a texture that we're going to call foliation. And it is a layering that you see in the rocks, but it's not layering like we see in sedimentary rocks, where we get deposition, where gravity is settling out these pieces and we get this bedded rock type. That's a different type of layering. Here, when you see layering like in this image here, this is not a sedimentary feature. This is a metamorphic feature. And that is because the rock originally started out like this, where it had elongated minerals that made up the rock. But under differential pressure, where we're crushing from one side, so this is associated with a collision of two plates because the pressure here is enormous and the differential pressure is very high. So the vertical pressure isn't very high, but the left to right pressure, if you will, from side to side as the two plates collide is extremely high. And what happens is our minerals slowly, because it's hot enough, these rocks, this is not occurring right at the surface. We crush these plates near the surface, the rocks are cold, they break. We get faulting, earthquakes. But deeper in the earth where it's warmer and the rocks are a little more pliable and the minerals can move and there's some fluids here, we can cause these minerals to line up. And as they line up, they give me this texture that we're going to identify as foliation. And when you see this texture, it's an indication of metamorphism, and typically it's an indication of regional metamorphism, where there's been a collision between two plates. This is the place where we get this high differential pressure. And so we want to be able to identify the texture, which we're going to call foliation, and that's going to help us figure out, in general, the big picture stuff, right? It gets really kind of specific when we look at the individual minerals that are generated from some of these events. But overall, in the big picture, you're really looking for two different types of texture in metamorphic rocks. Foliation, where there's been some alignment of minerals, usually associated with very high differential pressure, or non-foliated, where we don't see any foliation. And in general, that's associated with high temperature environments or contact metamorphism. Now, of course, there's always exceptions to the rules and things like that. If you don't have any elongated minerals and you crush a rock, it's hard to get foliation. So you certainly can get non-foliated rocks that occur under high differential pressure. But this level of class, I like to look at a rock and say, hey, it's foliated, non-foliated. Foliated means regional, high differential pressure, collisions of plates. Non-foliated means high temperature. So we're talking about coming into contact with some type of pluton or high heat environment. And so certainly we can get fluids that also accompany these types of events. And usually they play a role in almost all of these metamorphic events, right? Whether it's regional or contact. So there's always some fluids that are helping with the change that we see in the properties of the rocks that have been metamorphosed. And then, of course, one way to help us figure out more specifically what's happened here is we look at the minerals that show up under certain conditions. So yes, in general, we could say this is a metamorphic rock and give it a name. We might call it a schist. We might call it a phyllite or a gneiss. Those are metamorphic rock names that you'll learn about in lab. But we also see specific minerals forming that show up in my schist. And in this case, a garnet is a specific mineral that's showing up in my schist here. And it tells me some conditions under which I know only garnets form under certain pressures, which would give me a depth, under certain temperatures, which might give me a depth or related to some type of high heat environment. And so a lot of times we call these index minerals, and they can give me some more information about where this rock formed. And of course that helps me with my story. So these index minerals, these minerals that only show up under specific conditions, tell me something about what happened here. So they're recording all these different factors that influence the change in my rock. So look, general, same thing. And this can be, like I said, a little crazy. I'm trying to give you the really general story, and that is contact or regional, right? Contact, high heat, regional, high differential pressure. Here's a story. We have a collision between two plates. What do we see happening here? Near the surface, we get unmetamorphosed rocks because it's not hot enough. There's not enough fluids going on. But as we go deeper where the temperatures are higher and we're crushing the rocks because we have a collision side to side here, we get increasing metamorphism as we go down because temperatures are increasing, pressures are increasing. This is regional metamorphism over here. When I subduct and I have the formation of magma and that starts to rise and interact with these rocks, then I get contact metamorphism right around my pluton here. So we could argue that the contact metamorphism that we see is more local. And this is why we use the term regional when we talk about big collisions, because it affects a larger area. larger areas of rocks are metamorphosed during a regional metamorphic event than during a contact metamorphic event. Okay. What else we got? So we do get some low-grade kind of burial stuff where it's a low-grade metamorphism. There's a slight change here, but we usually don't focus on those types of rocks. And so we're just going to blaze over that. What else we got here? So this is just a repeat, kind of, right? So what is this I'm showing you? This is contact metamorphism. Why? Because high temperature is dominating. Okay? And so this is where you get that. Any type of molten rock that's moving in the subsurface that's coming into contact with rocks and not melting them can change them. And it's changing them through high heat. Okay? What else? And so, like I said, this is still video trying to be an overview, and I'm running long, so we're booking through here. But you certainly can get different grades, right? You select the most change closest to where the heat's the highest, and that's all this is showing you is there's a gradational change here, and different minerals form under different conditions. High heat minerals form close to the Pluton, and low heat minerals form farther away. What else we got? So just some more pretty pictures you can talk about. Usually we're creating non-foliated rocks here. That is because, right, the pressure, the differential pressure isn't driving the change here, it's the heat. So I don't get alignment of minerals because I don't have the conditions to do that. But under regional, which is here, and I'm going to argue also here, we get, even though the temperatures are high, it's the pressures that are doing the change, that I see the change in the rocks, and this is usually where we have convergent plate boundaries, and these are usually foliated textures that result from this, because we have that pressure, right, that's aligning the minerals, realigning them at depth, okay? And so that's what we're going to call regional. We get foliated textures. I talked a little bit about this in the video, but there's a degree of metamorphism, and we name the rocks based on the degree of metamorphism. A slate started out its life as a mudstone, but it hasn't been altered very much. So there's a small change, but we can still see foliation here. We can keep metamorphosing that rock and change it into a phyllite where it's more foliation has occurred. Larger crystals have grown. We could turn that into a schist. We could even keep going and turn it into a gneiss. So low-grade metamorphism, high-grade metamorphism. All foliated, so we would say that these are associated with some type of collision, where we have rocks here that have elongated crystals. As I crush them, they become aligned perpendicular to the greatest stress. So they realign and they show up like that. And I can identify that as a foliated texture. Not a layer, not a bed from sedimentary rocks, but a foliated texture resulting from high differential pressure. All right. Go, go, go. What else we got for you? We can get some unusual kind of metamorphic events. An impact site where meteorite has struck the Earth. Certainly you can imagine there's high temperatures and pressures. And this is near surface, but those high temperatures and pressures can generate some types of metamorphism. What else? So you go over this more in lab, but it's just telling you, showing some foliated, non-foliated, right? So we've got foliated, non-foliated. And so we have a bunch of rock names here, but usually we only focus on these two, quartzite and marble. And so these are rocks that started out as something else. They started out as a sandstone if it was a quartzite. They started out as a limestone if it's a marble. And so we look at the texture. How do we figure out what we have? Well, for these non-foliated rocks, we use composition to figure out what we have. For the foliated rocks, we actually kind of look at the degree of foliation. So when we look at foliated rocks, is it highly foliated? Was the foliation really easy to see, or is it very hard to see? That can give me some indication of the degree of metamorphism, and that can help me with the name. So let's see. Let me give you a few examples. So some images, same thing. You'll see this in lab, but this is an example of a quartzite. It also, this looks very similar to a marble. Here you don't see any lining up of minerals. This is a non-foliated rock. We would say contact metamorphism is probably what's happening here. How would we tell the difference between a quartzite and a marble? Well, a marble used to be a limestone, so we know it's made of calcium carbonate. We would use its composition, and we have a test for that, remember. Hydrochloric acid put on this rock. If it was a marble, it would fizz, it would react to the acid. That would tell me its composition, and I would know marble. If it didn't fizz, I would know quartzite, or I could try to scratch it with my steel now. It doesn't scratch because quartz, which is making up my quartzite, is harder than steel, and that could be a way that I could figure out what type of non-foliated metamorphic rock I had. We're using composition there. When we look at foliation, we're trying to make some assessment of the degree of foliation, and this is a slate, so it's pretty slight. We also see where the crystals get a little larger, and so we get this kind of shiny texture developing, and then even larger, so we get, this isn't the best picture ever, but we're also getting some development of minerals here. These are garnets that tell us something about the degree of metamorphism. And then the gneiss is usually the easiest metamorphic rock to identify because it's typically banded light and dark foliations here. Looks like layering, I know, but this was a force that crushed this and aligned the minerals in this direction, telling me that it was probably associated with regional metamorphism, where pressure was the dominant changer here, right? So I don't know that I brought this out, or I should have talked about it earlier, but the protolith, that's a term that's also brought up in the video. It is what the rock used to be before it became a metamorphic rock. So sometimes that's useful to figure out what did it start life as. And one of the more common protoliths is a mudstone, because I can take a mudstone and turn it into all of those things I just showed you: a slate, a phyllite, a schist, and a gneiss. And so we know that mudstones are common, right? Sedimentary rock at the surface. They certainly are common rocks that are forming in the ocean floor, and of course that gets subducted and crushed, and so this is why it's a common protolith, and then it turns into those other types of rocks depending on how deep it is subducted and the pressures and temperatures that it experiences. So I can get these different things here. Remember index minerals, just kind of a review there. And then this was this example of sandstone turns into a quartzite. A limestone turns into a marble. They're non-foliated. They can look very similar. I use composition to tell the difference here, as opposed to the foliated rocks where I'm trying to look at either index minerals or the degree of foliation. So more kind of examples of foliated rocks. We can take our mudstone, which is super common, and get a schist. We can even get a gneiss. Also, igneous rock like a granite can turn into a gneiss, also as another protolith of a gneiss. Just really, let's see, the last few, there are some other unique metamorphic events that we see, and one of those is where the fluids is the really big driver here. So certainly there's heat. A lot of times when we have a magma body, we get this circulation of groundwater, super hot fluids that circulate over and over and over again, and the movement of fluids is what's causing the change here. So we get a high fluid flow that can cause metamorphism to occur. So we get that at places where there's magma bodies near the surface that can interact with water, fluids coming off of the magma body, and the fluids that already exist here in the subsurface like groundwater. We also get that at mid-ocean ridges because we have that magma body there, and we get a huge circuit. Obviously there's a lot of water here. It's penetrating into the rock. It's getting superheated, and it's flowing over and over and over again, and that high fluid flow can cause metamorphism to occur. So it's a hydrothermal metamorphic event. And then finally, we do get some very localized metamorphism that occurs at fault zones. So you can imagine that when there's an earthquake and rocks are under extreme pressure, and then they fail and slide, that sliding motion generates a lot of heat, and of course there's pressure. So high heat, high pressure, we can get localized metamorphic rocks forming at these boundaries called fault zones where earthquakes occur. And so All right, I tried to make this short. It ran long, but big picture stuff. Remember what's causing the changes. How do we differentiate between regional and metamorphism, the textures associated with each, and what's the main driver of each, because that tells us a slightly different story of what happened and what the metamorphic rocks can tell us. Okay,